Hey there, Brad Guy here, and welcome to Pixels Refreshed. Today we're going to be looking at AMD's Accelerated Data Center Premier Keynote. So what this was a data center keynote where they're looking at targeting probably all of their EPYC platforms. They're looking at what their who their partners are going to be, what kind of big inroads they've made on data center, and you can read into this a lot about where their roadmap's going, where their architecture's going, what kind of advancements we can see whittle down into the desktop infrastructure or for Threadripper, and also just what the potentials for gaming in the future are. So without further ado, let's check this conference out.
Welcome everyone.
Lisa's got
thank you all for
pretty
joining
great
us.
stage presence. It's actually
Today
pretty
is all
amazing
about
to
the
see
data
how
center.
that's
And I'm
changed
looking
over
forward
time.
to showing you the next generation of AMD products.
Just the confidence of
that will
AMD
extend
going
our
from the
technology
earlier
leadership
conferences
over
to
the
their
coming
current
years.
ones.
We're in a high-performance computing megacycle, driven by the growing need to deploy additional compute performance delivered more efficiently and at ever larger scale.
I love
what
the difference between this and, like,
AMD,
let's say Intel's conference. Like, Intel felt like they were explaining everything from the ground up. Like, they felt like they were, they had to explain their last conference. I don't know if they would do the same thing when targeting data center, but they really treated you like you understood nothing about it, whereas Lisa's treating you like you understand already.
High-performance computing every day. We have made significant investments in multi-generational roadmaps to deliver leadership edge, networking, and cloud solutions. And in the data center, workloads are diversifying and becoming even more compute intensive. This requires specialized approaches to address these unique needs. We see the data center compute evolving into 4 distinct categories.
It's kind of interesting because I've always speculated that AMD's big advantage for these things is chiplets, and the fact that they have 2 things they're working on simultaneously. They have chiplets and they have Infinity Fabric. And the reason both of these are important in sync with each other is when you look at what she just said, how each of these require different types of acceleration, essentially. If you make like ASIC chiplets for each of those, you can connect them with Infinity Fabric, which is why these kind of cornerstones are so important to AMD's future.
General purpose computing covers the broadest set of mainstream workloads, both on-prem and in the cloud. Socket level performance is an important consideration for these workloads. Technical computing includes some of the most demanding workloads in the data center. And here, per-core performance matters the most for these workloads. Accelerated computing is focused on the forefront of human understanding, addressing scientific fields like climate change, materials research, and genomics. Highly parallel and massive computational capability is really the key. And with cloud-native computing...
So if I was to guess, and I'm probably wrong on this, and some developer would have to tell me where I'm wrong, but I mean, general purpose computing doesn't use as much of like FP64 or matrix multiply or those things. Whereas technical computing and accelerated computing use both of those. In accelerated computing, you get even more of those. You need your matrix multiplies. You need more of the potential AI, ASICs, or ways to accelerate those workloads, maybe even specialized workloads. Cloud native computing, I would guess, would need a lot of low latency and I/O, like input-output, and that would probably be what differentiates that workload, because it's almost as important how quickly the information gets in. Those are like my thoughts. I'm probably wrong about some of that.
Maximum core and thread density are needed to support hyperscale applications. To deliver leadership compute across all these workloads, we must take a tailored approach focused on innovations in hardware, software, and system design. Today, we're going to talk about our next generation data center CPUs and GPUs specifically designed for these workloads. This includes new cores, new packaging and process technologies, and new products. And we'll share with you how we bring it all together to power the exascale computing era. Now let's start with data center CPUs. We've made tremendous progress in the data center over the last 4 years. EPYC processors set a new trajectory for the industry in both performance and scalability, while delivering new levels of data security,
This is very true. For AMD, like their potential growth is almost infinite, whereas for Intel, their percentage growth or loss are minimal. It's like it's going to be some small percentage one way or the other. Where for AMD, because they had so little of the server market, anything they grasp seems like a massive scale increase.
And as a result, we're seeing growing customer preference for EPYC. In fact, to date, we have shipped more than 200 million AMD EPYC cores.
Well, that's a lot considering the fabrication. And I mean, obviously, data centers use a lot of CPUs, but 200 million is still a lot of cores to ship. I wonder how many wafers that would take at TSMC. So, I mean, obviously, I think that's a little bit more than I was expecting. I have no idea what NVIDIA and Intel's amount of cloud enterprise and HPC they're including, but that's, I mean, I wonder they must be much larger still, but I mean, billions of cores is still a lot to produce, especially considering most of them, well, except for Intel, are using TSMC.
Powering the daily computing experience for billions of people across the cloud, enterprise, and HPC. We've seen tremendous cloud adoption and have built a deep partnership.
This is a big deal. Like all of the largest ones there,
including AWS, Azure,
Amazon Web Server,
Google Cloud, Tencent, and Oracle Cloud.
A lot of people don't realize this, but Microsoft Azure is how Microsoft is pretty much buying all of the game studios for Xbox. They're thinking long term, and it's not Xbox money that's doing that. It's not like PlayStation is doing better than Xbox in general, right? I would say. But because Microsoft Azure is making, I think it's either the second or the third largest cloud and server provider, and because it's so big on those fronts, that the amount of money they're making from Microsoft Azure is probably one of their if not their largest source of income right now, and that's what they're using to buy all of these companies to expand their brand.
Earlier this year, we introduced 3rd Gen EPYC with leadership performance, core density, and power efficiency, enabling the largest cloud companies to deploy at scale with the best total cost of ownership.
I always wondered with the Xbox Series X if they designed that chip in mind, because they added a lot of custom instructions and for the machine learning, like the machine learning set and whatnot that they're building around DirectX 12 Ultimate for RDNA 2 and specifically for the Xbox Series X chip, always made me wonder if they were planning on doing some kind of server with AMD that was at least using those instruction sets, if not those outright chips, and just scaling lots of them, or a scaled up version of the chip that is already using the work so that they're laying the groundwork in one place and using it in both. I don't know if that's possible. There might be some caveats to that line of thinking, but that was something that I was curious about.
Today, I'm pleased to announce that Facebook, now called Meta, is the newest cloud partner.
That Meta thing still weirds me out.
EPYC processors.
It's like they're trying to dodge all the bad rep they got.
Together to jointly define an open, cloud-scale, single-socket server designed for world-class performance and power efficiency. We optimized 3rd Gen EPYC for their newest North Dome systems to deliver leadership performance per watt across major workloads. We'll announce more details together at the Open Compute Summit later this week. I want to thank Facebook for the partnership and strong engineering collaboration.
The biggest thing to take from this is the trust is growing. And when the trust grows, the infrastructure grows. Like, the biggest thing NVIDIA has going for it is trust. I feel like most of their partners both loathe and rely on them, and they trust them outright. And the big thing is that they're not willing to jump ship on NVIDIA for the most part because NVIDIA always delivers, and they rely and trust them, but they don't necessarily like them from what I've heard.
We're extremely excited to work with them to support their future data center expansions. This means EPYC is now designed into the data centers of 10 of the world's largest hyperscalers. Now, the performance, features, and efficiency of 3rd Gen EPYC are also driving strong adoption in the enterprise market. Some of the best-known Fortune Global 500 companies have deployed EPYC in their data centers to run their most important workloads.
This is a big change because
SAP is one of the leading producers
a lot of
software
companies
for
were
managing
very
business
wary
processes.
of it. And as more
Many of the
companies move
largest
over
companies
and
in the
more
world use
tools are
solutions based
developed
on
to help
SAP
deal with
S/4HANA.
it, the
Today,
more adoption
we're
will
very
grow.
excited to announce a new step in our partnership with SAP, focused on EPYC-powered infrastructure as part of the Rise with SAP offering, anchored by SAP S/4.
One of the big things that like working at small developers often is that if they start searching for things or they're looking to use like an API or an engine or something, and if they like start looking for hiring support or things like that, and there aren't people that are aware of it or aren't enough, is not an ease of hiring and it's not an ease of development, then they often ignore it. And that's one of the hardest things for new infrastructures or new ecosystems. Even though this probably operates mostly identical to an Intel server, the fact that there is enough change, and that would require probably different software experts, different kind of tooling in that regard, the more that... Sorry, my wife just came home and I lost my train of thought. So we'll pick off where I was and hopefully I'll find it again.
HANA Cloud. Together, we'll improve the TCO for our joint customers while also reducing the carbon footprint of the platform. And AMD expects to be one of the first adopters of S/4HANA Cloud solutions hosted on our AMD EPYC-powered infrastructure. I'm really thrilled to expand our partnership. While the momentum we've achieved with EPYC is great, we're always pushing the envelope on CPU performance and performance per watt. So let's get to our first major product innovation update today. Our investments and innovations in packaging have been a multi-year, multi-technology journey.
So they're not wrong on this. It's kind of interesting because anyone who's been looking at the roadblocks for this could have seen some of this stuff coming for a long time. So the first HBM products were... I believe they were AMD based. They might have been, but I know that obviously the Fury X was one of them, and then the Vega 64 and Vega 56 were also very early HBM products. I think before even in NVIDIA's, was it Tesla GPUs that also used HBM? And then they had several generations of HBM that was used afterwards by NVIDIA as well. Chiplets and 3D chiplets. So all of these were things that AMD was stacking to get ready for today. So all of these are being implemented.
Interposer technology in our GPUs in 2015, delivering industry-leading memory bandwidth in a small form factor. We set a new performance trajectory for compute in the data center and PC markets.
It's kind of interesting when you think about it because each of these individual products wasn't necessarily a gangbuster success for them, but each of them was a roadblock necessary for them to do what they're trying to do right now.
Which really enabled significantly higher performance and capabilities. And at Computex earlier this year, I showed you the next big step for the industry, one we developed in close collaboration with TSMC based on their 3D fabric technology, combining triplets with die stacking to create a 3D triplet architecture for high-performance computing.
I wonder what the limitations are for using 3D chiplets. There's always the risk of it insulating the layer below it, and causing heat issues, potentially. Although maybe there could be something about this that I'm not understanding. That would be my first thought, that could be a potential risk for it. But obviously, they could put like a ton of cache, because a lot of people don't realize that one of the biggest things that takes up space on like a CPU or just a die in general is cache. So if you had the ability to push your cache to another layer without affecting latency at all, that could do a lot. And it could mean big things for even like Vcache for RDNA. And yeah, there's a lot of potential there with cache.
Products. The first demonstration of our 3D triplet technology stacked cache memory directly on top of a Ryzen desktop prototype.
Yeah,
it was a significant increase in gaming performance.
It was the obvious choice there.
I'm excited to announce that we're bringing 3D triplet technology to the data center and our EPYC CPUs, adding a new 3D cache design to the leadership Milan product family. We're using an industry-first hybrid bond plus through silicon vias approach that provides over 200 times the interconnect density of 2D chiplets and more than 15 times the density compared to existing 3D stacking solutions. This enables a much more efficient and denser integration of our IP. The die-to-die interface is using a direct copper-to-copper bond with no solder bumps of any kind. This approach improves thermals, transistor density, and interconnect pitch over other 3D approaches, and is the most flexible active-on-active silicon stacking technology in the world, consuming less than 1/3 the energy per signal of microbump approaches.
I mean, the only two clients of TSMC's that would have the need for this tech would be NVIDIA and AMD, I would believe, for now. Like, Apple wants TSMC's latest node to literally dominate the entire mobile industry in terms of how their CPU, their SoCs look. But for AMD and NVIDIA, they're looking for server market share, and things like this are critical for it.
Our first server CPU with 3D triplet technology are codenamed Milan X. These processors have 3 times the L3 cache compared to standard Milan processors. At the top of the stack,
this is really going to show us more than anything how cache-starved chips are.
Memory bandwidth pressure
so I don't know what my audience is on this right now, but the way that chips typically work, and this is me coming through the pipeline understanding, is when it's looking for data, it needs to be broken up into chunks. Things need to be processed in memory. So if it's in L1 cache, which is a tiny, tiny cache that's right beside the chip, that's the best place for it. The L2 cache is usually shared between a smaller set, I believe. So if there are close cores, then they might share an L2 cache, and an L3 cache is a larger shared cache for all of these things. Ideally, everything would be an L1, but if it's not an L1, it should be an L2. If it's not an L2, it should be an L3. If it's not an L3, then it has to hit your memory, and that's much, much slower than any cache will be. So this is kind of showing us how often, this would be my guess, and I might be wrong here, but this would be showing us how often a chip is reaching for memory, and by eliminating that bottleneck, we're seeing how much these chips are because each one of these times that a chip has to go through these cache cycles and it doesn't have enough L3 cache, let's say, and it has to hit main memory. What's happening is you're getting a pipeline stall, and I've talked about this before. So all of those pipeline stalls accumulate through either the application you're running or the game you're running. So any performance increase we're seeing with Milan X versus base Milan is actually just the elimination of pipeline stalls.
This is latency, and that in turn speeds up application performance dramatically. Milan X is built on the same Zen 3 cores as our general purpose Milan processors with up to 64 total cores. It's the fastest server processor for technical computing workloads, with more than a 50% uplift compared to Milan processors, which are already the fastest in the market today. And they're fully compatible with 3rd gen EPYC platforms. With a simple BIOS upgrade, our customers can drop Milan X into existing platforms. This accelerates customer qualification and enables faster deployments.
See, this is a huge thing for AMD because
of software as is,
the fact that AMD is keeping the same motherboard infrastructure and you don't have to replace it every generation makes a pretty huge difference.
This is the 3rd gen AMD EPYC processor with 3D V-cache, Milan X. We have removed the lid from this package so that you can see the 6mm by 6mm SRAMs hybrid bonded to each of the 8 Zen 3 CCDs. To tell us more about the breakthrough per core performance that 3D V-cache technology brings to EPYC, let me welcome Dan McNamara.
Thank you, Lisa. The market traction with EPYC continues to accelerate, and we are pleased with our customer and partner adoption since our Milan launch. The next step in our journey is to deliver more differentiation and value with a focus on performance per core. So we are really excited about bringing 3D V-cache to market with Milan X. As a design target for Milan X, we zeroed in on technical computing applications. These are some of the most complex and demanding workloads in the data center. These applications are typically enablers of product design. Finite element analysis and structural analysis tools are used to simulate and improve the design of physical systems. Computational fluid dynamics is used to simulate physical interactions across a broad range of applications, from consumer product designs to aerospace engineering. Just as these software solutions are used to simulate the physical world around us, EDA tools are used to simulate and optimize chip design. While we were architecting Milan X, we looked deeply into how these applications behave and found that a large cache was critical to attaining better performance. More L3 cache ensures that critical data is closer to the cores, and that reduces latency in the system. So we saw a great opportunity to apply our innovative AMD 3D V-Cache to these applications and deliver a new level of performance to our customers. But before I show you what Milan X can do, let me first refresh on the Milan processors currently in the market. Today's Milan processors deliver clear performance leadership across a wide range of technical computing workloads. Here are benchmark results comparing our 32-core EPYC 75F3 versus the 32-core Xeon 8362 on key technical computing
It makes you wonder where these graphs are capped off, because this is a 40% increase, but it looks like it looks like a, I don't know, like a 2.5%, a 2.5 time increase. And same with this is like, obviously these graphs would go down to here, and then, I mean, it makes sense to crop them like this. It just doesn't seem right when you do it that way.
As you can see, Milan delivers distinct advantages compared to third-gen
40% is a lot.
processors, with anywhere from 33% to 40% uplift in performance. With this as a backdrop, I will show you how we're extending our leadership even further with Milan X. Let's take a look at EDA. Chip design is an iconic technical computing workload. It is highly compute intensive.
It's kind of interesting because I saw, was it Jim Keller was talking about this with Ian Kutras, about how current chip designs are being helped by AI, and they're using AI simulations to handle parts of the chip design in a way that even current chip designers aren't aware of everything in the process anymore. They just can't know everything in the way that they're setting up these chips.
On the left side, you see our leading third-gen EPYC server CPU. And on the right side, you see our Milan X CPU with AMD 3D V-Cache. Both are running Synopsys VCS. Each server is simulating an AMD RDNA 2 graphics core.
So these specific, when they do their demonstrations versus themselves instead of versus the competition, it always comes off as classier. Because NVIDIA is really good at this, in pretending that no competition exists and that they're competing with themselves. And, okay, you need competition to do good work, I would say, but it helps to, when you're presenting, you come off much classier when you're only insulting your previous work.
VCS
it's like a humble brag.
A model of this chip from source code, and then uses that model to simulate the design by running various tests. You'll see individual tests for the design change color as each is completed. As you can see, Milan X completes more tests in the hour, getting to full coverage in a shorter amount of time. These results show that the Milan X-based verification completes 66% more jobs than Milan. If you consider the competitive analysis that I started with, you can see that this new solution will bring the next level of value and performance to our customers. Users can finish their verification and get to market faster, or add more tests to further improve the quality and robustness of their design. Either way, Milan X delivers 66% more performance, and that will translate directly to the efficiency and quality of product.
So that's a lot of pipeline stalls. To imagine that each one of those, all the performance advantage is literally just it not having to search for main memory.
These applications are developed by leading ISVs for some of the simulations I just covered and many others.
When it's the same chip,
engineering engagements with key market,
the exact same chip that just has a much larger L3 cache, just shows how cache starved it was before.
They're all very excited about the capability and performance of Milan X. We're working closely with them to bring the combined hardware and software solution to market. As we continue tuning and optimizing these applications, we expect even more benefit for our customers. Our partners will be ready with certified and highly performant applications running on day one at launch. While we see tremendous value across technical computing with Milan X, we also see that a broader set of applications can benefit from a larger L3 cache. In today's data-driven economy, real-time decision-making is a must. In applications like data mining, risk analysis, and anomaly detection, getting to insights faster is extremely important. With Milan X, more data can be kept closer to the processor, driving faster outcomes. For media and entertainment, an industry that is transforming to deliver high fidelity in real time, large L3 cache will translate to more parallel live streams per server. And with AI, fitting more model weights and activations into the larger L3 cache can enable real-time inferencing. We are engaging today with ecosystem partners across these domains to develop turnkey solutions with increased performance and scalability. As you can see, we're excited about the impact Milan X will drive across the technical computing landscape, delivering value in three important ways: increased designer productivity, higher quality products, and faster product design cycles, leading to faster time to market. There is tremendous enthusiasm amongst our partners to bring Milan X solutions to market. Now, let me hand it back to Lisa to talk more about our partner plans.
Thank you, Dan. Now let's talk about Milan X Availability. One of our premier cloud partners, Microsoft Azure, is first to take advantage of the benefits of Milan X. To tell us more, here is Executive Vice President of Microsoft Azure, Jason Zander.
Thank you, Lisa. Microsoft and AMD share a vision for a new era of high-performance computing in the cloud, one defined by continuous improvements to the critical research and business workloads that matter most to our customers. We've partnered with AMD to make this vision a reality in Azure with our HP series of virtual machines, which offer up to 12 times the performance of other clouds and rival some of the most powerful supercomputers in the world. It's a fantastic platform for our customers to solve their HPC challenges radically faster and with greater cost effectiveness. Today, we're excited to announce the latest enhancements to the Azure HPC platform. Milan X processors are coming soon to third-generation Azure HP virtual machines. We're also announcing today a preview program for customers to get early access to Milan X processors in Azure. We're most excited about how these performance gains will help our customers and partners do their work better, as the significant improvements to memory latency and bandwidth with Milan X are a big win. For example, Ansys Cloud
This guy's the
is an
hardest guy to listen
integrated
to so
suite
far
of
this
engineering simulation
presentation.
tools and services, all hosted on Azure. In the early testing of HP series with Milan X, Ansys saw up to an 80% increase in the performance of their customers' aerospace simulations using Fluent.
And that
For
means
other
that
customer workloads, such as automotive crash test modeling, we're seeing up to...
What this is also telling us is about these workloads, because certain workloads, the reason cache would be more important is L2 cache and L1 cache are very small. So when something can't fit in them, then they need to be going into a larger memory system, right? So this kind of shows you the complexity of these workloads. So different workloads, they might be using a different instruction set, they might be using things like that. But primarily, my guess would be, and I'm not an expert on this, I'm just understand the basics a little bit. But the reason is these workloads essentially can't be broken down as small, so they're residing primarily in larger and larger caches. So when you see something that really benefits from an L3 cache, it's because most of it's hitting main memory more often than it would be preferred, really. So when you get something like 50% versus 80%, it's like different loads have different amounts of time that they need to hit the main memory. And if the type of instruction can be broken small enough to fit into the L1 or L2 cache, then the L3 isn't as necessary. But where you're going to see big performance increases or any computation that requires a little bit more size, that they can't break things down as small as quickly.
To a 50% higher performance. And that doesn't even begin to tell the story of the many-fold increase customers can experience over most on-premises hardware in use today. Finally, we're extremely excited about the ability of Milan X to advance the performance and total cost of RTL simulations in Azure. This is the key HPC workload for digital and mixed-signal silicon companies. Milan X brings some of the largest performance enhancements to RTL simulation in the modern history of silicon design. It's a giant leap forward for Azure to becoming the best platform in the world for silicon design, both now and far into the future. Our ongoing partnership with AMD and the innovations that we've seen along the way continue to move us forward and empower our customers to achieve more.
Thank you, Jason. We're so appreciative of the partnership between AMD and Azure, and we're excited about the preview with Azure HPC powered by Milan X. We're also working with the world's leading OEMs on Milan X. Milan X platforms will be broadly available from Cisco, Dell, HPE, Lenovo, and Supermicro. And I'm excited to announce we're on track to launch Milan X in the first quarter of 2022. Okay, so now let's turn our attention to accelerated computing in the data center. This is where the demand for compute power from scientists and researchers in order to analyze and make sense of incredible amounts of data at the highest of speeds
This is
has
going to
never been
be
more
using
important.
GPUs.
And GPUs are the accelerator of choice on these ultra-demanding workloads.
So GPUs are just,
We've been on a journey.
they're not as complex. They don't have the same quantity of instruction sets. When you look at a CPU, they have blocks for AVX vector instructions. They have blocks for SSEX instructions. They have all of these different little modules in a core that handle different instruction sets, that can do things more complexly, or they can handle very specific workloads, and they can break things down in specific ways. GPUs are just arrays with like a scheduler. If you're AMD and NVIDIA, they do the scheduler and driver, but you usually have a hardware scheduler that just sets things out to arrays of shaders, or whatever you want to call them. Compute units are the units with everything together. And anyways, they send them out to shaders. Shaders are just basically FP32 monsters. They're just arrays. So that when you see a GPU with 2,516 shaders, or 1,204, or even 11,000 shaders in the case of a 3090, that's what they are. They're just tons of little cores. All they do is process FP32 calculations. Some GPUs like Vega 64 and RDNA do half floats as well, which means they get double performance on that. And NVIDIA used to have that. I think in the 2000 series they did half floats. They cut it out with the 30 series, but it is available in their Tesla and their other lines, where you can essentially queue up two FP16s and do them for the cost of one FP32. And they also have FP8 and maybe even FP4. I don't even know, for even more performance.
We introduced CDNA, our first GPU architecture optimized specifically for the data center.
So CDNA is, from what I understand, a breakoff from Vega. Now, I'm different from most people in that I think Vega is a very underrated architecture. I think Vega was starved in PC, and it didn't show its legs well in gaming. I mean, it was a T-flop monster for the time, and some people will say things like all T-flops aren't equal, but the T-flops actually are equal. If you have a 12 T-flop NVIDIA GPU or AMD GPU, that part of them is equal. What isn't equal is all of the stalls in the pipeline that stop it from operating that way, or the other configurations of the core. So like, for instance, in the case with Vega 64, it only had 64 64 ROPs, and I think it only had 128 TMUs. So what ended up happening was NVIDIA cards typically had more of both of those. And they were clocked higher. So those parts of the pipeline would stall the Vega 64. And there were other software-based issues with engines and games that really didn't take advantage of some of the key features that Vega had. So it's a pretty good design to pivot to something like data centers. So I'm very curious to see where this goes, because I don't think it was a bad infrastructure by a long shot. I think that it was being starved, and maybe it needed more R&D a little bit, but I think there was a lot of promise with it.
And with it, we delivered up to 11.5 teraflops
I'm curious,
of FP64
obviously, with
performance with our Mi100
what they added
products.
was
Today we're introducing our first CDNA2 architecture-based products. CDNA2 was designed
matrix multiplies. They added specific hardware for matrix multiplication to help it catch up with NVIDIA.
AMD Instinct Mi200 GPU built with CDNA2.
Because when you get all of NVIDIA, when they talk about how many calculations, and it looks like an absolutely ludicrous amount of tera operations or TOPS or whatever, that's all through matrix multiplies, which I don't necessarily under the math for. You should ask someone else to explain a matrix multiply for you, or Google another video on it. But it's how they reach those numbers.
Architecture.
So now they have accelerated hardware for it in
delivers up
CDNA.
To a 4.9x increase in HPC performance over the competition. It's just a massive step. With this leap in capability, Mi200 will set new performance records across a broad set of HPC applications.
I'm very curious about this, because when you look at the previous data center GPUs, they would do okay in a couple of workloads. They would say things like this at conferences, but when you looked at the workloads, they would do very well in a couple workloads, and then they wouldn't do well in like 16 other workloads. And the biggest problem with all of this is CUDA is deeply entrenched. I talk to developers all the time, and when I talk to even like mobile developers, they'd be like, well, I want to go and simulate that in CUDA. And it's like, so the CUDA problem is a real problem for AMD to overcome, and it's one NVIDIA is not going to let go of. So unless we suddenly make a new standard that's so much more performant that everyone has to turn their heads away from CUDA, I don't see that happening anytime soon.
Mi200 delivers up to 1.2x higher peak flops of mixed precision performance for leadership AI training, helping to fuel the convergence of HPC and AI.
So it's 20% faster than A100 at AI.
Computing and AI platform, we're shortening the time between initial hypothesis and discovery.
I'm curious whether they're using accelerators from Xilinx. Because I know Xilinx is making AI accelerators, and I think that might be one of the reasons AMD is buying them.
With results overnight. Now let me show you the top of the stack Mi200 for the first time. It contains 2 CDNA2 GPU dies for a total of 50.
Okay, so this is nuts. And this is why AMD's previous investments were so critical. Chiplets, HBM, working on HBM with Samsung and with specifically on Fury X and Vega, and also Infinity Fabric. I've said before, Infinity Fabric might be one of the most important things AMD has ever done. And it was a bottleneck definitely in early Ryzen, and even in Ryzen 2000, it created more latency between cores than people would have liked. But it's good to own your bottleneck. And this is a bottleneck that they have and that they can improve whenever they want. So by improving Infinity Fabric, the interconnect between all of these parts gets better. Between the cores, between the memory, between all of that. So every time they improve Infinity Fabric, it makes all of their products better. And this is why it's a good bottleneck to have. It's bad when it's bottlenecking things, but it's a bottleneck they can improve without relying on anyone else.
8 billion transistors in 6 nanometer. This allows for up to 220 compute units.
220 compute units. How many shaders is that? 1 second. So there's 64 shaders in each compute unit. 220 compute units. This means 14,080 compute shaders, which is pretty crazy. So it's 7,000 shaders per GPU die.
And 880 matrix cores, which is 1.8 times more than Mi100. It also contains up to 8 stacks of HBM2E memory, making it the world's first GPU available with 128 gigabytes of HBM2E.
That's the thing with HBM.
That's 4x more capacity and 2.7x.
A lot of people don't understand how memory works, but the more modules you have, the more you increase your bandwidth, the more reach it can send outward.
And to see it in action, here's Forrest Norrid.
Thanks, Lisa. Today we're announcing 2 members of the Mi200 family. The Mi200 OAM, in production today, is a compact module that enables some of the world's most powerful supercomputers. And the Mi200 PCIe card
it's got a blower.
Will be available
it's got just a giant heatsink for server fans to blow through.
Beyond supercomputing. The Mi200 is amazing. Let's look at the 3 pillars that make it unique. The first is our AMD CDNA2 architecture, which is designed to do one thing extremely well: run compute-intensive HPC and AI workloads. The second is our innovative packaging technology that enables the Mi200 to be the world's first multi-chip GPU. Finally, our 3rd-gen Infinity architecture is delivering unified compute at exascale, with high-speed links and CPU-GPU memory coherence maximizing system throughput.
I'm curious with multiple GPU, because the reason multiple GPU was so hard in the past is because it was relying on PCIe, or whatever the interconnect was to synchronize those things. So when you have 2 GPUs side by side, the data rate between each of them gets out of sync, which is why you would get incorrect frame pacing, you get lots of like micro stuttering or frames being delivered incorrectly. I've had Crossfire and SLI setups before, and some games were so abysmal for them. Even with a lower frame rate, it was better to turn it off. So there always were the problems with it. But if you managed to have, I'm guessing it'd be interesting if you had it all on one die, and then if you shared the scheduler, if you pulled the scheduler out, I wonder if you could do that. There might be some technical reason why you couldn't, or if they just sped up Infinity Fabric to the point. Now, this is a problem for gaming, but for workloads like this, it's not really a big deal. It might put a little bit more strain on the CPU to be managing between the two. I'm curious, but that could be handled in the driver.
Lifting the lid, you'll see the multi-die construction of the Mi200. Dual AMD CDNA2 dies, 4 ultra-high bandwidth, low latency interconnects between them, 8 stacks of HBM2E memory, and another 8 Infinity Fabric links to connect to EPYC CPUs and other GPUs in the node. We put all of this together by continuing our packaging innovation. Today, we are introducing AMD EFB, Elevated Fan-Out Bridge, a silicon bridge technology. Unlike
a lot of this goes over my head.
embedded silicon bridge architectures, EFB enables use of standard substrates and assembly techniques, providing better precision, scalability, and yields while maintaining high performance. With all of this, the Mi200 OEM is shattering performance barriers and delivers a multi-generational leap in performance. The Mi200 OEM is 4.9.
This is interesting. I mean, looking at this, okay, so far the biggest caveats I've seen in the presentation is they didn't tackle AVX when comparing to Xeon, which has been a disadvantage for AMD for a while. I know that not all data center workloads use it, but it's still an important point. This is nuts. So when you're looking at, these are different workloads. This is what I was talking about before. You have your FP32, which is kind of like a baseline, what you understand for GPU calculation, right? And then you have your FP64, which is twice as complex. And what all floating point calculations are, this complexity is how many decimal points it does. So some things you need a lot of scrutiny for. It's like if you need to know whether when something falls, whether it lands on the corner of the table or whatnot, being 0.005 off of something could be enough for it to fall off the table or stay on the table. And that is when you need that level of complexity. If it doesn't make a difference, if what you're doing doesn't need that level of precision, it's not a big deal. So going higher precision, FP64, helps solve some of those problems. It just increases the amount of decimal places by a large margin. And then F64 matrix, these are the matrix multiplications. You can look at it as like a weird graph calculation, and it lets them get many more operations in specific workloads. So matrix multiplies are getting to be very important. I don't understand them fully. I'm going to look into that more.
9 times faster than NVIDIA's A100 GPU in peak FP64 performance.
I'm curious if there's any bottlenecks stopping them from realizing this power.
Requiring the highest level of precision, like weather forecasting. The Mi200's peak FP32 vector performance is about 2.5 times faster. These are the types of math operations used for vaccine simulations. Mi200 matrix cores deliver 95.7 teraflops of FP32 matrix operations, great for high precision machine learning and training. It also produces over 380 teraflops of peak FP16 and bfloat 16 performance, 20% more than the A100.
I don't think, like, NVIDIA can beat this. I know they can. I don't know if they can get away with releasing another product so soon with the shortages and the way that everything is. But I don't think NVIDIA was expecting them to catch up this quick. I think that was the thing. I think they thought that AMD would take a few years more to get these kind of numbers, whether or not it performs this way, and especially with CUDA entrenchment, whether it makes a difference. Because to be honest, AMD's GPUs could run twice as good as NVIDIA's in the data center right now, and they still wouldn't sell in as many as you would hope because of CUDA's entrenchment. So there would have to be some headway there first and some mindshare gains there first before any of that really changes.
And for data-intensive applications, Mi200 OEM has an industry-leading 128 gigabytes of HBM2 memory, as Lisa said before, that has a staggering 3.2 terabytes a second of total bandwidth. Put it all together, the Mi200 is showing incredible performance on HPC benchmarks and science applications. AMG and HPL benchmarks about 3 times higher than the competition. About twice the performance across a range of HPC research applications like OpenMM, HACC, and LSMS. The Mi200 is delivering the fastest application performance ever seen. Now let's look at another important research application, this time in molecular dynamics. Climate change, brought on by greenhouse gas emissions, is one of today's most pressing problems. To create more efficient combustion engines and fuels, scientists use high-performance computing to run simulations at the molecular level. To demonstrate the performance of the Mi200, let's look at a combustion simulation of a hydrocarbon molecule using LAMMPS. LAMMPS is an open source molecular dynamics code widely used by researchers all over the world. On your left, we're running LAMMPS on 4 NVIDIA A100 SXMs. On the right, in the same simulation, on 4 Mi200.
Curious if there was an advantage. So when they have 4 specific A100s and 4, I wonder if there's a scaling advantage AMD has versus doing it on 1. It's just a thought that crossed my mind, because it's one of these things that we see with GPUs that AMD's scaling to more compute units, it seems to be they don't lose as much. And the same with going to multiple cores on CPUs, is that Intel's scaling hasn't been as good from 2 to 4 to 6 to 8 cores as AMD's were, even when they were worse on a per core basis. So I'm curious if they're taking advantage of a known advantage they have in scaling.
This is a simulation of
but I know NVIDIA has crazy interconnects as well.
Detonation. It's about 20 million atoms and captures the first nanosecond as the chemical bonds begin to break. This typically takes days to complete. Obviously, we've time-lapsed the simulation here. The Mi200 completes the simulation before the A100 completed half. What does that mean? Scientists typically run hundreds or even thousands of these simulations to gain insights on new fuel alternatives or engine designs. With the Mi200, the time to analyze new compounds is cut by more than half, potentially reducing the characterization time from months down to weeks. This will dramatically accelerate the discoveries that reduce our emissions and carbon footprint globally. Now, we need to scale that performance to exascale. Our 3rd generation Infinity architecture is the key foundational building block. The Infinity architecture provides high-speed interconnects unifying the CPU.
So this is what I was talking about.
In the node.
The most critical thing AMD did was Infinity Fabric. I know that they're just calling it AMD's Infinity architecture now, but it just allows everything to talk to each other. And it's been the hardest thing for the competitors to replicate. I don't know. I mean, Intel has their mesh, and NVIDIA has done a lot with, I don't know the name of the company, but I think they bought them for NVLink and stuff like that. So they have, but I don't think any of it operates the way that Infinity Fabric does. So, and that maybe there's something that someone has to teach me about that, but I don't know. I think Infinity Fabric is probably one of the most amazing things in terms of also for eventually adding modules for accelerated workloads, or as soon as the faster they get Infinity Fabric, the greater potential AMD has to do anything, really. It opens up their entire universe, because the more things they can interconnect, the less they're reliant on their core chip infrastructure to save everything. They could just add a module or do more in that regard to improve their overall performance.
Deliver up to 800 gigabytes a second of aggregate bandwidth. It also unifies the CPU and GPU memory with coherent connectivity, reducing data movement and simplifying memory management. This dramatically increases developer productivity and streamlines the programmability of GPUs. Finally, this unified architecture provides a critical leap in making it easier to accelerate legacy CPU and GPU codes to more quickly tap into the power of the Mi200. Going even further, scientists are incorporating AI techniques now into HPC workflows to further accelerate data-driven research. AMD provides an open-source GPU compute platform, ROCm, that supports all of the major machine learning frameworks. That means developers can use the most popular AI frameworks on all of our Instinct accelerators, including the Mi200. And with ROCm 5.0, Mi200 will have the key ML models optimized, including ResNet, BERT, and DLRM. Now that we've showcased Mi200 performance and capabilities, let's hear from one of our first customers on what it all means, and not just any customer. I would like to invite Thomas Zachariah from Oak Ridge National Labs to share more about the beginnings of the exascale era with the Mi200-powered Frontier.
So this was the start of what made all of this possible for AMD.
Thank you for letting me be part of this amazing announcement of your GPU and CPUs, which is driving and powering.
So Oak Ridge through, what was it?
Now Frontier is going to be this amazing machine.
So a few years ago, I think was it 1 or 2 years ago, it broke that AMD got this contract for Frontier, which was supposed to be an exascale computer, I believe. But anyways, the big thing in there is that they also included a bunch of money for AMD to R&D and problem solve their way around all of the other problems in regards to this, which was GPU acceleration as well, probably alternatives to CUDA, alternatives to all of this, so that they could have a complete infrastructure and ecosystem. And this entire presentation is probably partially the result of having guaranteed funding for R&D on all of those fronts. And AMD wants to deliver. They're eager to prove that that was worth it, because that makes more customers for them. Where it's less, if NVIDIA or Intel got the same thing, it doesn't feel like they're as eager to completely change their perception outwardly. But for AMD, it's necessary.
An amazing scientific tool that is going to allow the dreams of many scientists from the world over to be realized, because they have this powerful tool that'll allow them to calculate and simulate important challenges. As we think about the most compelling challenges facing our generation, it's about energy transitions, it is climate change, and issues that we are currently facing as a society, tackling the pandemic. And Frontier is going to allow us to tackle these important challenges using the capability of the machine driven and powered by the AMD processors, which makes the Mi200 the most powerful processor that has ever been made available to the scientists. A single GPU is more powerful than the entire node of Summit, which is currently the fastest supercomputer in the United States. AMD has gone out of their way to make this a very efficient processor. So therefore, it makes Frontier a very efficient supercomputer. And so Mi200 is a culmination of a deep-seated partnership between AMD, Oak Ridge National Laboratory, and Frontier is a partnership between AMD, Oak Ridge National Laboratory, and HPE. But these important national challenges could not be achieved without commitment at the top. We are installing the supercomputer as we speak, and we are excited to make this supercomputer available to our scientists and engineers early next year. What Frontier is going to do is to accelerate science and scientific discovery so that we can continue to tackle the important challenges facing humanity.
Thanks, Thomas, for sharing your journey with us. All of us at AMD are extremely proud to be part of the efforts to bring Frontier, to bring the exascale era to life. On behalf of the engineering and support teams across AMD, as well as our strategic partners, the Cray team at Hewlett-Packard Enterprise, I'd now like to show you Frontier. Here is America's first exascale system, Frontier, powered by AMD EPYC processors and Mi200s.
So much of that
Frontier
is the
currently being installed
Mi200.
at Oak Ridge National Labs and will be coming online very soon and open to scientists next year. At AMD, we're proud to power the largest supercomputers, and with a growing list of partners supporting the Mi200, customers at all scales will be able to choose from a range of platforms and solutions to fit their unique needs. AMD is on a journey in accelerated computing. We will make
This is like the culmination of a
engines
journey.
available to accelerate targeted workloads. We will make them easier to use, and we will help solve some of the world's most challenging problems faster. We look forward to sharing more with you as we continue to push the boundaries in data center computing, making the best even better. Now, let me welcome Lisa back to close.
Thank you, Forrest. I have a couple more updates for you today. Now, you've seen this roadmap before. This is our server CPU roadmap that we've shown you for the last couple of years. We have executed very well to this roadmap, delivering Naples, Rome, and Milan to market on time and exceeding product expectations. The adoption of Milan has significantly outpaced Rome as our momentum builds. Today, I'm happy to provide an update on Genoa, which will be our flagship 4th-gen EPYC server processor. The engine driving Genoa is our next-generation high-performance core called Zen 4, built in industry-leading 5-nanometer process technology. 5 nanometer is doing extremely well. We've worked with TSMC to optimize 5 nanometer for high-performance computing, and it offers twice the density, twice the power efficiency, and 1.25x
Has
performance.
Apple moved off of 5 nanometer? I'm curious because it's all of this is supply constraints. So let me just check real quick. All right, one sec. Apple. So the new A16 chips will be on TSMC's new 4 nanometer process, apparently. So as this frees up, eventually we're going to see this open up. So AMD is looking to grab any of the 5 nm market,
and when introduced,
basically fab real estate as soon as it opens up.
The world's highest performance processor for general purpose computing. It's designed to excel across a broad range of data center workloads, from enterprise to HPC to the public cloud. Genoa will extend our performance leadership both at the socket level and the per core level, with up to 96 Zen 4 cores. And it supports next generation DDR5 and PCI Express Gen 5 memory and I/O technologies, combining next gen platform capabilities that fully complement the new Zen 4 core. The Genoa platform also includes support for the new CXL interface and will have breakthrough memory expansion capabilities for data center applications. And I'm happy to tell you that Genoa looks great. We're now sampling to customers and on track for 2022 production and launch. Finally, let's turn to the cloud. Cloud-native workloads are a fast-growing class of applications that are developed, deployed, and updated rapidly. These applications typically are very throughput-oriented and then can take advantage of a high number of threads. We have created a new version of Zen 4 specifically for cloud-native computing, and we call that core Zen 4C. It's fully software compatible with Zen 4 with specific cloud enhancements, including a new density-optimized cache hierarchy to enable additional higher core count configurations for cloud-native workloads that benefit from maximum thread density. And it also includes significantly improved power efficiency and breakthrough performance per socket. We're bringing the Zen 4C core to market with Bergamo, our new cloud-native server processor.
Moore's Law is going to be super happy. Tom from Moore's Law is dead, who's been talking about Bergamo for a while, Bergamo for a long time, and that was the only place I really heard it leak. So I don't think AMD is happy that it leaked out, but
Bergamo is a high core count, power efficient CPU purpose-built for cloud-native applications. It offers up to 128 high-performance
so that's where you see
Zen 4
128 cores
to deliver breakthrough performance and power efficiency for cloud-native workloads. And it
I'm
comes
curious
with all the same
with
features as
with this, what the reason is that Genoa is locked to 96 cores and Bergamo goes up to 128, especially because they're socket compatible. So there has to be advantages to Genoa. I wonder if there's some aspect of the CPU they're stripping out to manage to get more cores in.
Genoa, including DDR5, PCIe Gen 5, CXL, and the full suite of Infinity Guard security features. Bergamo is also socket compatible with Genoa with the same Zen 4 instruction set and can be deployed on the same platforms that our customers and partners are qualifying now. We're on track to ship Bergamo in the first half of 2023. So now you see the new and expanded AMD EPYC CPU roadmap. Our investment in multi-generational CPU core roadmaps, combined with advanced process and packaging technology, enables us to deliver leadership across general purpose technical computing.
If they're seeing with just the cache increase, that much performance increase, even going from, having Milan, Rome, all of that still on 7 nanometers and getting that much performance increase before we go to 5 nm, I'm curious this is just within next year. So it's like Milan X is going to be attractive for sure, but Genoa and Bergamo are going to be nuts. And the one thing I always say with all of this is I can never anticipate what's going to happen with ARM. I can follow the x86 race pretty well, but ARM is another thing, because there's always a chance that we'll find some other means to scale up really quickly. And this is why NVIDIA is so interested in the acquisition of ARM, because if anyone's going to sideswipe this entire market, it's some kind of ARM design.
And cloud workloads. We're extremely excited about the value that our next generation EPYC processors will deliver and look forward to bringing them to market. To wrap up, our CPU, GPU, and process and packaging innovations are enabling AMD to deliver leadership performance across the data center. As we come to the end of our time together today, I hope you now see why we're so excited about our vision and plans for the accelerated data center. You can count on us to continue to push the envelope in high-performance computing. Thank you for joining us today.
Okay, so that was the AMD Accelerated Data Center Premier Keynote. And there's a lot of takeaways from that. I'm curious what all of this means for the future. We get some insights to where it's going, what's going to happen with 5nm, the importance of cache, how important cache is, how much some applications are currently cache starved, and that's what's limiting performance, that the chips are already much more capable than you're led to believe, and we're literally just hitting time stalls in the pipeline as it's waiting for a slower memory interface, that these are just slowing it down from doing more computation. And just unburdening those increases performance quite a bit, but then increasing those and increasing IPC of the general chip is going to make a huge difference as well. Sometimes they include cache changes as IPC, when I don't know if I count them exactly the same. I would personally think of like IPC changes as changes where the core design actually processes things faster, but I mean, a lot of that nowadays is actually reducing latency between individual parts of it. So AMD is definitely in a good position to take market share from Intel, especially as adoption grows and smaller players get more interested in and not having to troubleshoot a lot of the problems themselves, because what they need to see is all of the big players using AMD silicon and knowing that they can get support from other people who have invested time and resources into it. Once that happens, it's going to make a big difference in terms of the adoption. In regards to GPUs, they could have, like, I swear AMD could have GPUs that were twice as good and they still wouldn't perform quite as well as NVIDIA, just because of the market share and mind share that NVIDIA has. But NVIDIA doesn't have that same mind share It has it with the people that use the software, but it doesn't have it with the companies. The companies have kind of a love-hate relationship with NVIDIA, as far as I'm aware, where they wish that they didn't have to work with them. If there was a competitor that they could trust the same, they would love not to. I know TSMC's in the same boat. For TSMC, it doesn't make a difference whether NVIDIA or AMD does well in server market share, because they make the money either way. So what matters to them is what partner would they rather work with. And I think, to be honest, their relationship with AMD is better than it is with NVIDIA. NVIDIA has done underhanded things to them in the past, and if anyone's going to turn on them, they know NVIDIA will. So TSMC's volume is maxed out regardless, and it's really going to be more of a, if TSMC could rely on AMD actually getting that mind share and getting that, I think that TSMC would be happy to go with AMD on those, but they're not going to lose their biggest customers either. They don't want to lose Apple, they don't want to lose NVIDIA entirely. And they're not going to risk anything with NVIDIA unless they know AMD has more than mind share. It has, I wonder how much of this is tied around AMD's names. There's been a bunch of times that I've wondered if AMD would have done better if they completely dropped the name and came up with a new company at this point in time, because they're reliving through all of their past baggage, trying to define a new future for themselves. And that's been somewhat difficult for them, but they're doing incredibly well with the hardware. And I think that they'll continue to do well with the hardware. And we see things like Oak Ridge and Frontier. All of that funding is going into R&D. You can notice a difference in terms of R&D, less holes in their process. When you look at their CPU thing, when they're showing that graph, there were areas where there was significant weakness in their hardware designs. But when you look at what they're showing that they're actually matching or exceeding on virtually every type of computation. And that's something that AMD has been very weak at in the past. So they are using the R&D wisely, and I think they're doing a really amazing job. I'm curious to see what Intel and NVIDIA's presentations are like. I'll definitely watch those when they come up. Maybe I'll do a video with those if people enjoy this one. I hope it wasn't too long. I hope you had a good time. If you have any questions or if I said anything terribly wrong, please leave comments and I'll respond to them below. And I hope you liked the video, and I'll catch you on the next one. Feel free to click like and subscribe, and later.